In this video, we want to show you how to design, build and control a four-legged, electrically driven robot. The goal of our research is to make such machines robust, versatile, fast and energy efficient. Before discussing robotic devices, let's have a look at nature. This is a dog called Rocky. He has 4 legs attached to a main body, each of which allowing movement in all directions. To do this, he needs control of at least 3 degrees of freedom. Using this as inspiration, we designed a leg with a similar kinematic structure, driven by a set of electric motors, which collectively allow actuation of the required 3 degrees of freedom, namely hip abduction, hip flexion, and knee flexion. Mounting 4 of these legs, additional motor controllers, and onboard computers, we get our first quadruped robot, Olaf. To make Olaf walk, we have to coordinate all 12 joints correctly. Firstly, we have to keep the center of gravity over the support polygon to avoid falling or tipping over. Secondly, to ensure forward motion, the feet have to step ahead accordingly. The onboard computer calculates the desired joint position using inverse kinematic methods and sends them to the motor controllers several hundred times a second. The motor controllers can then precisely track the joint positions over time. With his joint mobility, there are many other things Olaf can do. He can stand up, recover from a fall as a result of tipping over, and even move on steep inclinations or loose ground. In this case, he applies a special turtle-like crawling gait. All these maneuvers are relatively slow and thus created prior to application. In this state, Olaf is not programmed to react to unforeseen events. Additionally, since the robot is designed mechanically stiff, it behaves more like a table than like a dog. The rigid characteristics are further exposed if Olaf is subject to impact forces. The peak loads occurring due to the ground contact interaction immediately destroy the gearboxes. How can we engineer a robot that interacts with the ground similar to a real dog? To analyze this, we first have to understand the actuation principles in and around the joints of legged animals. The rigid links, in this case bones, are manipulated by a muscular tendon system. In contrast to standard robotic devices, both muscles and tendons act as compliant elements, sustaining large impact forces and storing potential energy whilst falling or running. This then allows the animal to interact in a compliant way with the environment and locomote very efficiently. While the leg is compressed, energy is stored in the muscles and released again before liftoff. To adapt these mechanisms to a robot, we had to rethink the mechanical design. Instead of connecting the motor and gearbox directly to the link, as done in Olaf, we included a spring in series. This is called a series elastic actuator. Similar to nature, the spring protects the gearbox from impact forces and allows for energy storage. Measuring the spring deflection and applying Hooke's law, we get precise information about the actual joint torque. By moving the actuator correctly, the actual joint torque can be controlled. Based on these principles, we built a new quadruped robot with steel springs in all 12 joints. All the actuators are tightly integrated at the hip joint to make the moved segments as lightweight as possible. The low inertia at the end effector allows fast leg motions and reduces impact losses. This new robot is called Starlet. Let's go back and drop some dogs. Okay, the robot doesn't brake. Instead, he passively bounces around due to the mechanical springs, something we don't see in the natural counterpart. To mitigate this bouncing, Starlet has to be controlled continuously throughout the whole drop. Let's have a look at this process in detail. First of all, we have to detect contact. After making contact with the ground, the joint angles, body acceleration, and rotation rates can be measured. With this information, the base position can be precisely estimated. To control the robot, we virtually apply forces on the main body. This allows us to imitate the required dynamics needed to stabilize the robot's orientation and position. These forces are distributed to the contact points and subsequently to the individual joints. Applying this principle, we can achieve quite natural behavior. Starlet can react to lifting its foot and pushes. Furthermore, we can start to become more dynamic and fast in our maneuvers. As an example, Starlet can perform a trotting gait. He can do so even if there are obstacles in its way. In such maneuvers, the spring in series contributes to the passivity of the system. The springs in the joint are compressed after landing to store energy and released again before liftoff, increasing the running efficiency. Despite all these efforts, there's still a long way to go until legged robots will support us in our daily tasks.